Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Joseph Lykken, who's come across to us from Chicago, where he's at Fermilab. Joe did his BA at the University of Minnesota, and then a PhD at MIT. After that, he went to Los Alamos as a research associate, and then spent time at the Santa Cruz Institute for Particle Physics, before joining Fermilab in 1989. Since then, he's risen through the ranks to now become the deputy director there at Fermilab, and he's the chief research officer as well. Joe's a collaborator on the CMS instrument at the Large Hadron Collider. He's also a fellow of the American Physical Society and the AAAS, and he has published on a wide variety of theoretical physics topics, including weak scale superstrings, supergravity and Kaluza-Klein states and large dimensions, neutrinos as messengers of charge conjugation, parity and time reversal violation, and also observations, of course, of the new boson at 125 GeV with CMS. In May, he published an article titled Supersymmetry and the Crisis in Physics in the Scientific American, which some of you may have read, and that's going to be the topic of, part of the topic of what he's going to talk to us about today. So please join me in welcoming Joe.
Well, thanks, Adrian, for that nice introduction. I'll give you a little outline of the talk. There's the Scientific American article with perceptive reader. I'm going to go through a little bit of how we discovered the Higgs boson. I think it's a very interesting story, even if you've heard parts of it before. And then I want to talk about the future, about what it is that we're trying to understand now, having made this discovery, and what the Higgs boson might be related to, including the fate of the universe, but also things that are of interest to particle physicists, such as dark matter and supersymmetry. So let me start with how we made this discovery in the first place, and I'll explain a little bit also what I mean by we, because it's a very large number of talented people that were involved. So I wanted to start out with something that would be of interest to people that would come to a SETI talk. So I thought, if you're interested in SETI, you're interested in advanced civilizations on Earth-like planets. So let me show you one. So here's the Earth-like planet. And the advanced civilization is called Switzerland. I don't know if you've heard of it. As you can see, they have a very large particle accelerator there. You actually don't see it if you're up in the air because it's underground. It's about 100 meters underground. It's called the Large Hadron Collider. It's 27 kilometers around. And at 4 points around the ring, you have these gigantic detectors, of which you see one here called the CMS, which is the experiment that I've worked on, which is a 15,000-ton piece. It's $1 billion piece of fancy electronics that's designed to capture all the particles that come out of these collisions. So that's the basics behind CERN and the LHC and CMS. And I could just show this movie. You'd probably be happy if I just showed this movie for an hour, but I'm not going to do that. So let me get back to the slides. Just to get an idea of scale here, if you see this picture of the LHC, compare it to Lake Geneva and the airport, and you get some idea about how much this costs, for example, because it's bigger than an airport. So if you just think about the civil construction of building something of that size, you can see what a huge scientific project this was. If you go down in the tunnel, you see this. This is, first of all, the world's narrowest fire engine. And you also see these blue cylinders are superconducting magnets. So these are very powerful and very large and heavy superconducting magnets. They go all the way around the 27-kilometer ring, and they are cooled down to a couple of degrees above absolute zero, which that in itself is an incredible feat of engineering. Some of those magnets were built at my laboratory, Fermilab, in the good old US of A, and we shipped them over there and put them down in the tunnel. And this was taken a few years ago when they were first installed, and as the Fermilab representative, my job was to put the American flag sticker on the magnet so that we would get credit for it, which we did. The other view I wanted to show you here was this one, which in addition to the magnet, which is the blue thing, you see to the left of it are the white pipe And the white pipe is carrying liquid helium, because if you want to cool something down and keep it, this is thousands of tons of material. So you're trying to keep thousands of tons of material a couple of degrees above absolute zero. And to do that, you have 20 tons of liquid helium that goes in the big white pipe all the way around the ring. So this is the world's largest refrigerator in addition to everything else that it is. And that's actually relevant to the story that I'm sure if you were paying attention to the news reports you heard about. They turned on the machine in September 10th of 2008. They got the first beam. Everybody was happy. They're all clapping, shaking hands. And less than 2 weeks later, the machine exploded. This was first reported by CERN as a helium leak. This is how you manage news stories of this type. But what actually happened, and it took a while to reconstruct what actually happened, was that these magnets are very powerful magnets, and they're connected together at joints that connect them, which are basically soldered joints. So these are big, slightly fancy soldered joints. One of those joints failed when it had 8,700 amps of current running through it. So as you might imagine, that's a bad thing. And these magnets dump their stored energy mostly as heat. It sent a pressure wave both directions down the tunnel. It vaporized about a ton of that liquid helium that I was talking about in a few seconds. It's a good thing there was nobody down in the tunnel, because first they would have started to talk really funny, and then they would have died, because of course the helium displaces the oxygen out of whatever area it gets into. So it was a good thing nobody was down there, and it destroyed about 53 of those huge magnets. Those magnets weigh about 10 tons each, and they were tossed around like they were little children's toys. So that was bad, and it took about a year to recover from that. It turned out that the experiments, the big detector experiments, were not too unhappy about this delay, because they had their own problems. So this is one of the other large experiments, ATLAS, which again, you see this is $1 billion worth of fancy electronics. This little pipe here is where the beam goes into the detector. There's a collision in there, and then the detector is trying to capture everything that's coming out. They were happy to have the extra year to make their detector work, as was the experiment that I worked on, CMS, which again was incredibly complicated. Here I've shown you the CMS detector. This is just a piece of it, but it's pulled out so that you can see it has a magnet too. This round cylindrical thing is another superconducting magnet that they use to bend particles in order to measure their momenta and their charge. And that magnet, although it's not the world's most powerful magnet in terms of the magnetic field, because it's so huge, it's actually by far the world's biggest magnet in terms of the energy that gets stored into it when you charge it up. It's an absolutely amazing. They were very, very careful the first time they turned it on, because when you turn on a magnet that big, things move. And you better know how much they're going to move and which direction they're going to move when you do that. And in fact, they were a little bit off, and there was a little bit of nervousness when they first turned this thing on. It's got a lot of energy in it. So as you might imagine, this is not something that you can do at home. It takes the effort of thousands of people with all kinds of different abilities. Just the CMS collaboration, so this is one of those 4 experiments that I showed you before, is more than 3,000 people, scientists, engineers, computing scientists. About 1,000 of those are students. They come from 193 universities and labs in 40 countries, including countries that are mortal enemies, are working together in one experiment for the LHC. And I also want you to understand the role of the US in this. This, of course, is an international project. It's based in Europe. It's actually not just Switzerland, it's on the Swiss-French border. So half that ring I showed you is in Switzerland, the other half is in France. So truly international in that sense. But the US contingent is huge. We're about 1/3 of the CMS experiment. We're the largest national contingent. It's about 1,000 people from the US just in the CMS experiment, and also a lot of people in the ATLAS experiment. And again, it's students, it's engineers, it's all kinds of people from 93 universities, 7 labs, including my lab, Fermilab. So we take a lot of the credit for what happened. Another way of seeing that is to go down into the CMS control room and see who's actually working there. So this was the scene in the CMS control room on the first evening when they got high energy collisions, which happened, again, as you see, more than a year that it took to recover from that accident that I talked about. And if you ask who was actually running the experiment, well, it was 2 Americans, one from Caltech and one from Cornell. Why were the Americans running the experiment? It's because they had the experience, because we had been running a very similar but lower energy machine called the Tevatron at Fermilab, and these physicists had experience on that machine. And so when the LHC turns on and they say, well, who knows how to run an experiment like this at a big machine? it was the Americans that had the experience, and so they were the ones that were down there running things from day one. This is also the spokesperson is shown here, Jim Verdi, who is not American. He's from Imperial College London. But the spokesperson's job is to just sit in his office and wait for something good to happen, and then he comes down to the control room with a bottle of champagne and hands it out to everybody. It's a slightly different kind of job. I mentioned a little bit about computing, just to give you an idea of what the computing was like when CMS turned on. We were facing a data rate that was on the order of a petabyte a second. So just think about what you do with a petabyte of, talk about a fire hose of data. A petabyte a second is a lot. Even by the standards of your local businesses here in Mountain View, that's a lot of data. The other thing that the LHC was very important for was the birth of what we would now call cloud computing, of massive distributed computing, both for storage of all this data, but also processing the data, because there's no place in the world that has enough computers to process this much data. So in fact, at any given time, when we were processing the LHC data, we would have something like 500,000 jobs running on different computers scattered all around the world. So what were we trying to do that was so hard that it took all of this computing and all these thousands of people? Well, we were trying to discover the Higgs boson, among other things. And these Higgs bosons are pretty hard to make because you don't have them, they're not sitting around. It's not that you find them, you have to actually make them. And how do you make them? You make them from very high energy collisions, in this case of 2 protons. And if you're lucky, about 1 in 10 billion times that you collide very high energy protons, you'll make a Higgs boson. So suppose so that's a needle in a haystack, 1 in 10 billion. So suppose the 1 in 10 billion, you've got a Higgs boson. How do you see it? Well, that's also slightly challenging because it only lives for about 100 yoctoseconds. Does everybody know how long a yoctosecond is? Okay, good. It's a very short period of time, as you know. So then it decays into other particles. So you don't see the Higgs boson, you see the other particles. And there's lots of different ways it can fall apart. And you actually discovered it in 2 different ways, which I'll show you in more detail here, which turned out to be the easiest ways to look for it. One of the ways you can look for the Higgs boson is when it decays into 2 very high energy photons, which we usually use the Greek letter gamma to represent. So here's an actual, what we call Higgs candidate event. I say candidate because you can never tell for sure that a particular collision produced a Higgs boson. You can only make a statistical statement that it was probably a Higgs boson. And as you see in this particular collision, you made some stuff. So the beams came in this way, they collided, they made some stuff. But among the stuff they made were these 2 very high energy photons that are represented there by the green bars. And that's one of the ways that a Higgs boson can decay. And by getting enough of those, you convince yourself that you're seeing Higgs bosons. Another way you can do it is what we call the golden channel, where the Higgs boson actually decays into 4 particles. And here the 4 particles are what we call leptons. But leptons just mean electrons. They're antiparticles called the positron. And then they have relatives called muons, which also come in 2 different charges. And you can make 4 of those particles in different combinations. And we call that the golden channel because, as you can see in this picture of the collision, it looks pretty clean. It's an event in which it's pretty clear what's happening, what's coming out. There's not a lot of mess there. There's not a lot of extra junk to worry about. This is slightly misleading, though, because what I've shown you is a slightly cleaned up version of what the collision actually looks like. Here's that same kind of golden channel collision, but now I'm showing it to you very, very close to where the actual beam was. So again, the beam is coming this way. They smash together. And what you see here is you see 24 yellow dots. That's because we have so many protons going one way and so many protons going the other way that when they pass each other, we don't just get one collision, we get a bunch of collisions every time this happens. In this particular case, we had 24 collisions that happened at the same time, and only one of them made a Higgs boson. And you have to convince yourself then that you're actually tracing everything back. All those lines there have to be traced back so that you understand that you're actually got 4 different particles coming out from one collision instead of, say, 2 particles from one and 2 particles from another one. And the thing, without getting into all the fancy electronics, the electronics doesn't see lines, it sees dots. It's a bunch of little sensors, and the sensor either gets a hit or it doesn't get a hit. So just imagine that the way they got all those lines was by taking a bunch of dots and then solving a connect the dots problem that produced all of those lines. So think about writing the computer code that takes 10,000 dots and figures out how many each one of those producing a line like that. And the wow is supposed to be That's a SETI joke. Does everybody get that joke? Yeah. Okay, good. Somebody else has to explain it to. So this is that was an animation. I'll play it again because it only takes 12 seconds. This is an animation of the data that we got in this golden channel where you produce the 4 leptons. And this is a little bit complicated to interpret because there's 3 bumps here. This bump comes, which has now gone away. This bump comes, the first bump comes from a particle we already knew existed called the Z boson, which used to be an exotic, interesting, heavy particle, but now it's boring because we already knew it's there. There's a second bump that comes from the fact you can actually make 2 of those Z bosons, and then you get a bump that's at about twice its mass. And then there wasn't supposed to be anything else left. That was all the particles that we knew about, all the bumps we could explain. And the discovery of the Higgs boson was the fact that there was the 3rd bump, which is represented here by the red line, but of course you don't see the red line. What you actually saw was those dots, which are the data as collected in different bins of energy coming from the 4 leptons. So the wow is the fact that you get a bump in a place that you don't expect a bump. And you have to be, of course, very sure that you didn't expect a bump from some other source like that. So on July 4th, which was a coincidence as far as I know, because the Europeans were the ones that determined the date, they announced the discovery. Just to make us a little bit more difficult for the Americans, it was at 2 a.m. Central Time. So we had to get up very early at Fermilab, and you see we look kind of like zombies here. But nevertheless, it was very exciting. Again, plugging the Americans. This is the CMS spokesperson who's from UC Santa Barbara. This is Fabiola Giannotti who's from CERN. So the 2 big experiments simultaneously announced their discoveries. Peter Higgs was in the room crying, as well he should be. As it says at the bottom here, he never expected to live this long. His prediction of the Higgs boson came in 1964, so he had to wait a pretty long time to see this verified. And of course, the press went crazy, as well they should. And the other thing I wanted to emphasize here was, of course, at the press conference, you see the spokespeople of the experiments, but who actually made the discovery? Who was actually down in the trenches looking at the data, making the detectors work, fixing things when they broke at 3 o'clock in the morning? You know, who were the people that actually did this? It was done by young people. Of those thousands of people I talked about, 1,000 of them were students. Most of the rest of them were younger researchers. This is a representative photo of the people that actually made this discovery. And of course, that makes sense. The young people, they're smarter and stronger and better in every way. And so they're the people that actually did all this. And it's incredibly exciting, of course, to be 24 years old and discovering the Higgs boson. So now I want to get into the second part of the talk, which is explaining what we think we might be learning from the fact that there actually is a Higgs boson. And to do that, I have to make a little bit of the connection between Higgs bosons and Higgs fields, this idea that you have particles. Higgs boson's a particle, but then you also have fields that go along with that. So let me start with what the Higgs boson is supposed to do. Why did Peter Higgs say, oh, there's got to be a Higgs boson, and by the way, you should name it after me? Where did that come from? It has to do with very interesting ideas that we see in particle physics that have to do with symmetries. So we have in particle physics a standard model that explains all of the interactions of all the fundamental particles that we know about, all the elementary particles that we know about. So there's quarks, there's the electron, its friend, I talked about the muon, the Z boson that I mentioned. There's photons from electromagnetism, there's neutrinos. So there's all these elementary particles we know about. And we have a theory that explains how they interact with each other in a mathematical way. And it's a very well-tested theory. We know it's right to a part per thousand in many cases. And this theory can be written on a cocktail napkin if you're sufficiently patient. And the reason it can be written so concisely is because its properties are very, very, very strongly specified by symmetries that are built into it. So I could almost say to you, oh yeah, make a theory that's consistent with quantum mechanics and relativity and has the following symmetries. And if you're in the know of particle physics, you can write down something immediately that's basically this standard model of particle physics. It's specified so strongly by those requirements. So that's a remarkable fact of nature that these symmetries are operating in such a fundamental way. But on the other hand, the world we see doesn't look very symmetrical, right? It looks very messy. And this is a much broader question that goes beyond particle physics, which is how do you start with laws of nature which are simple and symmetrical and have beautiful properties like that and end up with such a messy universe? It's good that the universe is complicated and messy, because otherwise it would be really boring and things like life would not exist. I think the first person that really had a lot of insight into this was Philip Anderson, who's not a particle physicist. He's actually a condensed matter theorist. But he wrote an article which I highly recommend in Science magazine called More is Different, trying to understand how do you get from simple laws of nature to complicated things like life. And he said the first part of this step is the idea of what we now call spontaneous symmetry breaking, which is that when you have large systems, an example of a large system in his way of thinking is a glucose molecule. At some point, these systems become large compared to sort of the basic scale of quantum mechanics and subatomic physics, and they start to forget about the fact that the laws of nature are symmetrical because they have, as you see, they have all these complicated features, and at some point it's just too complicated to try and maintain all the symmetries, and instead you start to get essentially random, complicated looking properties. So it's a feature of things as they get larger that they also get less symmetrical. So that's a very interesting idea, and he's a Nobel Prize winning theorist, so he knows what he's talking about. But equally important was the realization by this gentleman on the right, Mr. Nambu, that in addition to the fact that molecules get large and complicated, the vacuum of space, empty space, is a large thing too. And it has properties because of quantum mechanics. It has stuff in it. It has what we call virtual particles in it. So it's big. It's the vacuum of space. It fills all of space. And it's complicated. And because of that, it behaves more like a glucose molecule than what you would normally think of as empty space. It actually has complicated properties, and in particular, it can violate the symmetries that we think are built into the laws of nature. So that was an idea that was around when Higgs and his collaborators started to think about this in 1964, and more or less simultaneously over the course of the year 1964, a bunch of people had various ideas that put together is now what we have as the Higgs story, but Higgs got his name attached to it, so he got most of the credit. And the basic idea that he had was that you could have a particular kind of field that could fill space. That field would have interactions with itself. And because of that, even in empty space, without talking to anything else, without there even being anything else in the universe, it could break some of these symmetries that are built into the laws of nature in empty space. However, if you did have other things around besides this Higgs field, it could have an effect on them, and the effect that it could give to other particles is the thing that we interpret as mass. So you have a Higgs field, it fills what you would think of as empty space. You can't see it, but it has an effect, and the effect is what we interpret as mass in other particles. So that was his basic idea. It sounds like kind of an abstract idea, but he did note in his 1964 paper, oh, by the way, if there's a field there, there also has to be a particle, because in quantum mechanics, we find that every field has a particle. Electromagnetism is a field, the photon is the particle. There's always every time you have a field, there's a particle that has to exist too, and so he noted in his 1964 paper that somebody should go out and look for these bosons. And indeed that happened, and it took many decades for it to happen, but with the help of 10,000 people and a lot of your tax dollars, he eventually got his trip to Stockholm. So okay, there's a Higgs field, there's a Higgs boson. The Higgs field is everywhere. It's giving mass to other particles. What else is interesting about this Higgs? Now that we've got our hands on it, what else can we say about it? Well, one of the things that I'm going to show you is that the Higgs field existing everywhere in empty space could also have an effect on empty space. And one of the things it can do is make the universe unstable. So that's an interesting question, and I'll show you what our thinking is about that. Another question you can ask about is, well, the Higgs is invisible, at least it was until recently. Is it related to other things that are invisible, like dark matter? We know most of the matter in the universe is also invisible. We haven't been able to get it in the laboratory yet. So is it related to that? Is the Higgs related to particles which have mass but have weird properties related to mass? In particular, neutrinos are particles which we now know have mass, but they have teeny, teeny, tiny mass. So it sounds like they talk to the Higgs, but in a way that's very different from the way that other particles talk to the Higgs. So can we understand that? Can we understand whether the Higgs is responsible for the fact that there's matter at all in the universe? Why didn't the universe start out with matter and antimatter in equal parts and they all annihilated a long time ago and there's nothing left? We don't live in a universe like that. That sounds like a simpler universe. It sounds like a more symmetrical universe, but we don't live in that kind of a universe. And then if you answer all those questions for extra credit, you can figure out whether the Higgs is related to cosmic inflation and dark energy. But I'm not even going to talk about that because I have nothing intelligible to say. So let's start with vacuum instability. So how does that work? So this idea of force fields that exist in empty space, it's a weird idea if you think about it. It was invented by Michael Faraday, and his contemporaries in science thought he was nuts for this because it doesn't sound like science, right? It sounds like the ether. You say, oh yeah, there's a field, it's invisible, it's everywhere, don't worry about it. We're kind of used to that with magnetic fields because, for example, the Earth has a magnetic field, but the magnetic field has a couple of properties that are very reassuring. First of all, it has a source, which in this case is the Earth, so there's a reason why it's there. And secondly, it has a direction because that's how the compass tells you which direction it's associated with it. So the Higgs field is a little different from that. It's a field that's everywhere and it's invisible, but it doesn't have a source. It's its own source to the extent that it has a source at all. And it doesn't have a direction. So you can't make a compass that points in the direction of the Higgs field. So people thought Faraday was crazy, but the Higgs field is even crazier than that in the sense of the invisibility. Furthermore, as I said, the Higgs field, whatever it's doing, it, to some approximation, doesn't care about the existence of anything else but itself. So it's a field that somehow is turning itself on. So we believe that in the early universe, there was a time when the Higgs field actually turned itself on, and it did it through a process that didn't rely on anything else being there. So it's a very different from the other kinds of interactions of matter and energy that we're used to. And the way we describe this has to do with what's a physicist in the 1960s called the Mexican hat potential. That's probably not politically correct nowadays, but the name has stuck. And it's basically, the way it's usually explained is this is supposed to be the Mexican hat. It's got a brim, and then it's got this bulge in the middle. And if the Higgs field were not turned on, it would have a value 0. But if it is turned on to some non-zero value, that's the thing that we think actually happened at some point in the early universe. And what this Mexican hat is supposed to be telling you is that you can get in a situation where it's actually energetically favorable for the field to be turned on rather than to be turned off. Think of this as the energy of the system. It's a lower energy to be turned on in this case than it is to be turned off. And that goes against our usual intuition because you usually think it's lower energy to turn things off than it is to turn them on. But that's not always the case in physics. You can have cases in physical systems where it's lower energy to turn it on rather than to leave it off. So then you could ask the question, well, okay, so maybe I buy this story. There's a Higgs boson, so I guess there's a Higgs field, and the Higgs field turned itself on, so it has some value, which would be represented by being at the bottom of this little red depression here. So it's got some value now, so that's where we are now. And is that where we're going to stay? Is that really the place that the Higgs field wants us to be? Or is there some other place that we could be that's even more energetically favorable, and maybe we'll get there someday? Now that's a calculation you can actually do using the standard model of particle physics and using just ordinary quantum theory. There's a calculation I can do that tells me what it is that the Higgs field wants energetically. And this calculation we're now able to do because we know enough about the properties of the Higgs field. And this is what we find. We find that, yes, it's true that we are here with the Higgs field that's turned on, but really what it would really like to do is turn on to a much higher value. It could lower its energy even more by turning on to a much higher value than the value it has now. And the only thing that's saving us is the fact that there's this bump in the middle. So there's an energy cost to getting from where we are now to where the Higgs field would really like to be, which is going over this hill, energetically speaking. So that's somewhat reassuring, but unfortunately in quantum mechanics, if something is, a hill is not enough to prevent something from happening. And eventually, there will be some kind of unlucky quantum fluctuation that will cause us to do a process called quantum tunneling that will get us from the false vacuum that we're living in now, apparently, to the real vacuum that the universe wants to be in, whatever that might be. So how will that happen? Well, the way that would happen would be that at some point, somewhere, spontaneously out in the vacuum of space, in between galaxies somewhere, just through some funny little quantum fluctuation, there'll be a little bubble that will form. And that little bubble will be living in, with the Higgs field turned on to a higher value, and that will be a lower energy state than the ordinary vacuum that surrounds it. and so the bubble will expand. And it will expand at the speed of light, and it will keep doing that, and nothing will stop it until it completely wipes out everything that's already here, and we will enter a new era for our universe. So that's a little bit alarming, and in fact, when this came out, this was known for a long time to physicists, but it wasn't known to the press until fairly recently. So of course, once Fox News got this, Higgs boson may spell doom for a universe. Yeah, so sorry about that. So there's a lot of, if you actually estimate the numbers, most likely it'll take 10 to the 100 years for this to happen. So probably you shouldn't sell your house and you should continue to pay your taxes. On the other hand, it may already have happened and the bubble, it might be on its way here now. And you won't know because it's going at the speed of light, so there's not going to be any warning. Now, more interesting to us as physicists is the fact that when you do this calculation, which again is a calculation using standard physics we know about, it turns out that we're right on the edge between a stable universe and an unstable universe. That's essentially why it will take so long. If you change those numbers a little bit, we would have been wiped out already, or it would never happen. But we're sort of right on the edge where the universe can last for a long time, but eventually it should go boom. So that's very interesting to physicists because, why is that happening? Why are we right on the edge? There's no principle that we know of that would put us right on the edge. So one of two things is happening here. Either we're living right on the edge of between a stable and an unstable universe, in which case we'd like to explain that, or the calculation is wrong. And this is all, everything I just told you is just the wrong calculation. But in that case, there's something else that's supposed to go into the picture that must have to do with the Higgs boson, and it must be very fundamental because it has to change this fundamental property of how the Higgs boson works. And I have two candidates for you for that. One is dark matter, which I already mentioned, and the other is supersymmetry, which I'll mention in a moment. So let me first talk about dark matter. If you go to the CERN laboratory, they have all the streets are named after various things. And there's an intersection of physics and astronomy, which is a good place to talk about dark matter. Dark matter has been known for a long, long time, since actually 1930s. Fritz Zwicky was the first one to suggest that there had to be a lot of dark matter to explain the way that galaxies and galaxy clusters behave. And we now know we have vast evidence of the fact that there's dark matter dominating the universe, and we could even map out where the dark matter is. So there's no question that the universe is full of dark matter. On the other hand, we would like to know how dark matter interacts with ordinary matter. It does interact with ordinary matter gravitationally. This we know, and that's how we know the dark matter is there in the first place. Doesn't interact with ordinary matter in any other way. Maybe it doesn't. Maybe we're just unlucky and there's this whole sort of shadow world that only interacts gravitationally with us, in which case in the laboratory we're never going to see dark matter. On the other hand, we know that there are some pretty weak forces out there in the universe, and maybe the dark matter interacts through one of these weak forces, and that's the reason we haven't seen it yet in the laboratory, because you have to do a very, very sensitive experiment to see that the dark matter particles are there. There's dark matter particles, going through this room right now. In your hand right now, there's 100 dark matter particles passing through your hand. So there's lots of dark matter particles around. It's just a question of whether we can detect them. So we know that there are weak interactions. One of them involves this Z boson that I already mentioned. That's actually an interaction of the Standard Model whose name is the weak interaction. So that's a weak interaction. We know it exists. But also the Higgs boson mediates a force. So there's a Higgs boson, there's a Higgs field, there's also a force associated with the Higgs. And that's a weak force. And we know its properties now, at least some of its properties. So it's also possible that dark matter interacts with ordinary matter through the Higgs boson. And that's an interesting thing that we can start to explore. So now I can ask, well, what does this tell me about people that are actually looking for dark matter? So this is a different kind of experiment. I'm not trying to make the particles the way we do at the LHC. I'm just trying to detect the dark matter particles that are whizzing through this room. How do you do that? Well, the first thing you do is you go find a mine somewhere, because if you don't do that, you're going to be completely overwhelmed by cosmic rays. There's all kinds of energetic particles that are just from ordinary radiation that are whizzing through this room. And your sensitive detector is going to be completely overwhelmed by those unless you go down in a mine. So you go down in a mine. This is a mine that's in Minnesota. You go deep down in the mine. And then you build the most sensitive kind of detector out of whatever material you can, stick it down in the mine, and then you make as many of those detectors as you can in order to try and increase your sensitivity. So this is an example of one of those. And then in the end, they either see something or they don't. And these dark matter searches so far have not seen anything, or they haven't seen anything conclusive. And then when you don't see something, you make a plot like this, where you say, well, if the particle had a mass in a certain range, the dark matter particle, and if it interacted with matter by a certain amount, which is represented here on a logarithmic scale, so this is 10 times weaker, 10 times weaker, 10 times weaker, 10 times weaker. If it were above a certain amount here, we would have already detected it, because we have the sensitivity of our detector that we should have seen a signal. So lots and lots of possibilities for dark matter particles, which are perfectly good theoretical possibilities, and people wrote lots of papers like me saying, oh yeah, you're going to find the dark matter and it's going to be here. Those people were wrong. But it's still possible that we will find dark matter particles. And what's interesting has to do with how you map this sort of plot into how strong the forces would be between dark matter and ordinary matter, depending on what was responsible for those forces. So I mentioned the Z boson as an example of that. If the Z boson was interacting between us and dark matter, we should have seen a signal a long time ago. So that's ruled out. If the Higgs boson had turned out to be much heavier than it is, this is about 4 times heavier than it actually is, we'd also be pretty unhappy because, remember, this is a logarithmic scale, so this is sort of 100 times weaker than what we know how to detect. But in fact, there is a Higgs boson with this mass, and with this mass, our prediction is that if the Higgs boson is what talks to dark matter, these experiments should see a signal in the next round of experiments that happen in the next few years. So again, this is kind of a funny technical coincidence that we have the technology now to get to this, just the interesting region now, if the Higgs boson talks to dark matter. So that's pretty exciting for the people doing dark matter searches. And then the last thing I wanted to mention was supersymmetry. So this is an idea, again, that goes back to this notion that the standard model of particle physics has lots of symmetries in it. And so people have thought about, well, maybe there's more symmetries than the ones that we know about, and maybe those symmetries are important for understanding certain things that we don't understand. And this has to do with the idea of having what are called partner particles, which at first sounds like kind of a funny idea, but it actually goes back to Paul Dirac, one of the inventors of quantum theory, and he had predicted circa 1930 that just the fact that you have a quantum world that obeys the laws of relativity from Einstein predicts that every particle has to have a partner. There's not just one set of particles, there's 2 sets of particles. There's what we now call matter and antimatter. And that was a very, very strong prediction for him to make based on just what I would think of as kind of mathematical consistency. But in fact, his prediction was correct. And we now know that every particle either is its own antiparticle or it has an antiparticle partner. So that was a statement that just had to do with the consistency of the theory. Supersymmetry is the idea of putting in even more partners. So in addition to antiparticles in supersymmetry, every particle has what's called a superpartner. And this is a way of putting more symmetry into the laws of nature. It affects the quantum world in a way that we think makes it better behave and makes it easier to understand a lot of the properties that we see in particle physics. It's, for example, makes it easier to understand the Higgs boson. It predicts that dark matter should exist in the first place. And the other thing it does is it gets rid of that vacuum instability that's going to kill us all in 10 to the 100 years. So there's lots of reasons to like supersymmetry. And even experimental physicists like supersymmetry because it makes predictions. It predicts that for every particle that we've seen, and we spent 50 years finding all these guys, there's a whole other set that they haven't seen yet. So all these guys can go out and do experiments and make discoveries and win Nobel Prizes. So it's the greatest thing ever. Here I have to apologize because the only chart I had of the superpartners was in German. So we have quarks apparently is quarks in German, but leptons are leptonin. And then their superpartners are called squarks and sleptons, which are here called sleptonin. So that's the idea of supersymmetry. It predicts all these new particles, all these partners, and all we have to do is go out and look for them. So, of course, we're not stupid. We went out and looked for them at the LHC, in the LHC experiments. And we even got the theorists to tell us some numbers. So here are some predictions from a famous particle theorist. These are in the units we like to use for mass in particle physics, which are GeV. So he had the guts to say, okay, you're going to find this superpartner called the galeno will be no heavier than 1300 GeV, and the other superpartner, the superpartner of the top quark, will be no heavier than 400 GeV, and you can't lose. You've got to go out and find those things at the LHC. So we did that, and you see the results. And again, these results are not discoveries, they're limits. And what this one is telling you is, just by coincidence, I think, is that this superpartner of the galeno that he said couldn't be heavier than 1300 GeV, we've now eliminated all possibilities lighter than 1300 GeV. So that's bad for him. And then for the stop, which is the superpartner of the top quark, he said 400. Actually, we ruled out almost everything up to about 600. So this was bad for the fans of supersymmetry. And the crisis in physics, which this is the Brazilian version of Scientific American, in case you don't get that. This is very discouraging for those of us that are fans of supersymmetry. It's, of course, a very important experimental result because it shows you where not to look. But I think we're sort of a schizophrenic now, because it's true that you didn't find the thing you were looking for in the most likely place for it to be, but it doesn't mean that you should give up. And in fact, we have examples in history of people that built particle colliders to trying to discover something, and they just missed it. In fact, the Tevatron at Fermilab just missed finding the Higgs boson, and there was a previous collider at CERN that was called LEP, which also just missed finding the Higgs boson. And it's only in retrospect that we can go back and say, hey, you guys, if you would actually run an extra 2 years, or you'd put a little extra money into upgrading your system, you could have found the Higgs boson. So this could be what's happening with supersymmetry, that in the first run of the LHC, which remember was affected by the fact that the collider blew up, so they actually ended up running at lower energy than they were supposed to, it could be that they just missed it, and when they turn on next year, we expect next spring at higher energy, these superpartner particles could show up right away. So we don't know, so it's where people are worried, but we don't know what's going to happen in the end. So what I want to leave you with is not really a conclusion. I think the LHC has only just begun what it's going to tell us. We found the Higgs boson, which was a big deal, but we're still trying to understand what it means, and we're also trying to understand all the other things that go along with it. We're going to run this thing, I think, for another 20 years. So this is very much the beginning of the story, and I've shown you some directions that that story can go in, but I think there could be surprises that nobody has even thought of. So I think it's not the end, it's the beginning. And this is the attitude I always have. Thank you.
I'm sure there's lots of questions, so just put your hand up and I'll come around to you, and I'm going to start with the first question, Joe. Is it possible that we might that there may be multiple particles making up a Higgs boson at the moment?
Yeah. So there's two related things we're looking for. One is the Higgs boson really an elementary particle, or is it a composite that's made out of other things? And that you can tell basically by looking at its properties. So now we're trying to collect together a large sample of Higgs bosons and study their properties. And that's one of the things you can get at, is whether or not it really is an elementary particle, or whether we can make it fall apart into other things, or show us some evidence that it's made out of other things. The other thing we're looking for is whether there's more than one kind of Higgs boson. So this is a new kind of particle. Nobody ever saw a particle like that before. Maybe there's 10 of them. In fact, supersymmetry predicts that there should be 5 of them, of which we've only found the first. So there may be a bunch of Higgs bosons, and we just have to look for them.
Hi, over here.
Okay, yeah, thank you.
Sure. So in the scenario, which might happen sometime in the next 10 to 100 years of vacuum instability, if that bubble that statistically is likely to form in the middle of intergalactic space hits ordinary matter, I get the impression that it's bad, but is it like crossing the streams in Ghostbusters, or what exactly happens to ordinary matter in this scenario?
Yeah, the wall of that bubble is, so what is that wall? It's the Higgs field going from a smaller value to a much larger value. So first of all, there's a lot of energy in that wall. And secondly, if you think about what the Higgs field does, it gives other particles mass. So if I look at the particles in my body and say what would happen to them if a bigger Higgs field went through them, the particles in my body would get much more massive. In fact, it would be almost to the point, this is the part of the calculation, we don't quite have the numbers, but it's close, at least close to being this, that it could turn me into a black hole. It could make the particles in my body so heavy that I would collapse into a black hole. It's close to that. That's bad. That's bad.
You know how the Higgs boson is self-sourcing, right?
Yeah.
It kind of reminds me of the sun for some reason, and how the sun is self-sourcing. And can you tell me the relations between the Higgs boson and maybe similarities to the sun?
Yeah, I mean, there is a similarity, right? So the sun powers itself from fusion. And the reason and it lasts for billions of years, right? So how can it last for billions of years? The reason it lasts for billions of years is because there are all these, sun is mostly hydrogen, a bunch of protons. Those protons, there's a lower energy state they can be in where they fuse into a deuteron, which is a proton and a neutron. And the reason why that doesn't happen all at once is because converting a proton to a neutron is something that you can only do through those weak interactions I was talking about. So it's actually very difficult for that process to actually turn on. So the sun is able to do that because there's so many protons and they're so densely populated that a few of them are fusing together at any given time. But the whole process requires billions of years to play out. But it's sort of like the Higgs in the sense that at the end of the day, the reason this is happening is because there's a lower energy state that the whole sun can be in, and it eventually gets into that lower energy state. The state where they're all fused is a lower energy state than the state it started out in. So its energetics wins in the end.
Yeah.
Yeah.
A question about the mass of the Higgs boson. Was it what was predicted or slightly different, and what implications does that have?
Yeah, that's an interesting question. So supersymmetry doesn't precisely predict the mass of the Higgs boson, but it predicted that it should be relatively light. So roughly speaking, it predicted it should be between about the mass of the Z boson, which is 90 GeV, and at most about 130 GeV. So that's a fairly narrow range because other theories said the Higgs boson could be 10 times that. So we found it at 125, which is close to the high end of what supersymmetry said. So you could say it's a triumph for supersymmetry because it's in the range supersymmetry said. On the other hand, it's on the high end. And that makes people a little worried that maybe our knowledge of supersymmetry is a little screwed up and maybe there's some ingredient we didn't put into this calculation.
You mentioned that in the spring, LHC will be cranked up to a higher energy level. Will that also require that the magnets be charged up to a higher field level?
Yes. So it really comes down to how many amps are going through those connections. So the reason why we ended up running at 7 and 8 TeV instead of 14 TeV is what it was designed for, was just the current. It's just the current going through the connections, and they're worried about that. Now they have checked all the connections, replaced all the bad ones. They've also put in systems where if you have an explosion, the explosion won't propagate down the system as easily. So explosions will be more contained. Even with that, they're not going to go to 14 TeV because they're too scared. They're going to go to 13 because they think it's a safer operating point. But nobody knows. Nobody's cranked it up to 10,000 amps, and you don't know until you do it. Somebody's got to turn the dial and say, okay, let's go for it.
Yeah, I'd like to hear you elaborate on the dark matter. That if I look in the laboratory and do a cabinet experiment, I don't see any evidence of unknown matter. If I study the motion of satellites in the solar system, there's no evidence of some. Apparently, if you get to the galaxy level and you look at rotations of things, you have unaccounted for matter. So you said
Yes.
you knew where some of this matter is, so I don't see it in the lab, I don't see it in the solar system. Where is it?
That's a very good point. So dark matter is not the dominant form of matter around the Earth. It's not the dominant form of matter in our solar system. It's not even the dominant form of matter in the plane of the Milky Way. So you have to go outside of that. And if you say, let me take our galaxy and go out a radius that's 5 times bigger than what we actually see in terms of stars, it's only on those scales and larger that you find out that you missed something and that the dark matter, whatever it is the dominant form of matter. So that's not too surprising from the fact that dark matter interacts apparently very weakly with ordinary matter and with itself. So it doesn't clump together as well as ordinary matter. So it doesn't, the stars and planets of the Milky Way, they form this nice almost flat disk. And it's because of the fact that they're interacting with each other in a fairly efficient way. The dark matter is more spread out because of the fact that it doesn't interact very much. So it's not too surprising that you have to go out to really large scales, but it is true that that's the only way you can see it.
I have one question. There are 4 forces in nature: the weak force, the strong force, gravity, and electromagnetic force. How does the Higgs field fit into this equation?
Yeah, so those 4 forces that you mentioned, 3 of them are what we call gauge forces. So they're carried by in principle, what should be massless particles that are similar to the photon. The W and the Z bosons have mass, but they get their mass from interacting with the Higgs field. Then there's gravity, which is a special case. And then the Higgs is also a special case. It's not a force carried by a photon-like particle. It's also not gravity, but it is yet another way that you can generate a force. In fact, this is a very old history, because when people were first trying to figure out gravity in this language of particles and fields, there was a guy named Nordstrom who had a theory of gravity that was based on exchange of particles that were like the Higgs boson, instead of the way we think about it nowadays from Einstein's theory of general relativity. In fact, he was a competitor of Einstein, and Einstein said his theory was crap. And in fact, the famous experiment where they looked at the bending of light by the sun in order to test Einstein's theory of gravity, it was not only testing Einstein's theory, it was ruling out Nordstrom's theory that was more based on a Higgs boson-like force. So you can have forces like the Higgs boson, it's just that we had no evidence of them until recently.
When I look at that graph of the curve of the where the symmetry breaking is, I see a very shallow dip, which suggests that there should be kind of variations along the shallow dip. Something out there would be moving a little this way and a little that way. Is there any? Does that produce anything?
So, in the very early universe, that would have been true at some point, because when this field turned itself on, it presumably didn't turn itself on at exactly the same time by exactly the same amount everywhere. So there was some period in the early universe where there were unevenness of exactly the time you were talking about, and then it must have smoothed itself out. And one of the challenges for cosmologists is to go figure out how you can see the remnant of that. We call that the electroweak phase transition. This was the actual. It's like a phase transition of melting or anything else when the Higgs field actually turned itself on. And that was a messy event, and it must have left consequences that in principle we should see, but nobody has seen them yet.
The original specification for the superconducting supercollider was significantly more powerful than what the LHC is presently. Is there some of this older technology be adaptable to the LHC to scale up its energetics?
Yeah, it's interesting. The SSC was supposed to be 40 TeV instead of 14, so about 3 times the energy. It was using less powerful magnets, but in a bigger ring. It turns out one of the things, so we're thinking now about the future and thinking, what's next? What do you build that's next after the LHC? And people are talking about something that is more along the lines of the SSC, but now really being driven by the idea of cost. Because the real problem with these big colliders is how much they cost. The LHC cost $10 billion as built, which means if I wanted to build it starting now, it would be $20 billion by the time I inflate it. So, okay, maybe you can get a consortium of the whole world to spend $20 billion on a machine, but you're not going to get them to spend $100 billion or $200 billion. So if you want to sort of get to the next level with these kinds of big machines, you have to figure out how to make them cheap. So forget the fancy technology. I want to know what's the cheapest way I can dig a hole and put cheap magnets in it that I can make a big accelerator out of. And that's the real challenge now.
Okay. Does the Higgs boson obey the Klein-Gordon equation?
Yes, it does.
Okay. So is the instability in the Higgs boson due to the existence of negative energy states that positive energy bosons can decay to?
Yes. So it's related to that, which is another way of saying that it's related to virtual particles and the effect that those virtual particles have on the Higgs field itself. In fact, most of it has to do with virtual top quarks, because top quarks are the heaviest known elementary particle. They talk to the Higgs boson in the strongest way, and it's actually the effect of virtual top quarks that's responsible for a lot of what you were looking at there.
Okay, if you have any more questions, Joe's going to be around for a little bit to answer those that you're not willing to get recorded. So that's fine. Joe, we have a special SETI mug here.
Great, thank you.
It's dark. It could be dark matter. There's going to be some dark matter.
There's dark matter in the cup.
Right. Please join me in thanking Joe for his great talk.